and thanks for inviting me for this talk. So this talk is on multi-objective optimization using a learning-based approach. And this is joint work with my students, Mridul and Chinbo, and my collaborators, Tian Lan at George Washington and Amrit Bedi in Army Research. So multi-objective optimization has been a widely studied area. There has been tons of books on this topic for the optimization perspective. The key difference that we are talking about in this talk compared to tons of work already done in the area of multi-objective optimization is that when we talk about learning domain, the model of the optimization is not known a priori. So you kind of have to learn the model and make decisions in the model. So it becomes kind of a explore exploit setup where you have to spend time on learning model more accurately and then making decisions on the model at the same time. So multi-objective optimization has been used widely in autonomous decision making. The key metrics for any type of system is to manage all the robustness, resilience, flexibility, agility of the system, mainly to have good performance as well as managing the risk of the system. So let's take some examples. In networking area, you have delay decreases as the power increases. If you spend more power into the system, your delay can decrease. Similarly, if you have higher power, you can get better spectrum efficiency, better rates. So we try to optimize multiple objectives like delay, power, throughput. These are some of the key objectives, and we need to trade off the different objectives based on our function of the overall system utility. In general, if we talk about any type of network use, we again have some form of delay, throughput, the cost for waiting customers, and those are the type of metrics that govern general queuing systems. So in general, not just in networking application, every engineering applications has multiple objectives. We need to care about multiple things in order to come up with efficient decision making. So let's put it more formally. So you have different objectives. So reward of a particular objective. So let's call you as either a user or an objective. So you have a reward of an objective at time t. The joint reward, if it is linear, would be sum of, it could be a weighted sum. So we could include the weights inside. That doesn't change the structure. So weighted linear rewards of different objectives over different times. So that is basically some form of linear reward structure. Nonlinear reward structure is you have the overall reward of first objective, overall reward of k-1th objective, and overall reward of kth objective. And we are optimizing a nonlinear function of the rewards of different objectives. Okay, so think of the first reward as the sum of delay, kth reward as sum of throughputs, and k-1th has sum of costs over time. So a function of overall delay, overall throughput, overall cost, and things of that nature. In the standard reinforcement learning, the function is assumed to be linear, while we consider a general nonlinear function of different objectives. Let's consider an example, a concrete example to understand the type of applications for this particular form of multi-objective optimization. So a simple example that we come up with is a base station scheduling example. So in base station scheduling, you have a base station, let's say cell tower of AT&T or Airtel. We have multiple users connected to the base station. At each time, the base station decides which user to give the resources to. It could be just time or time frequency blocks based on whether we are using 2G or 4G. So alpha KT is the resource allocation, where if a resource is given to user K at time T. The reward, the different objectives here are the rewards to the different users. So reward to user 1 is objective 1, reward to user 2 is objective 2, and so on. So reward to user small k is the average rate it gets. RKT is the rate user k gets if it is given the resource. Alpha is an indicator whether the user k is given the resource at time t or not. So this is the overall aggregate rate user k gets, and this is the average rate dividing by t that user k gets. So the objective of user small k is given inside, and the overall objective typically is based on a fairness metric among the different users connected to the base station. And one of the fairness metrics is called a proportional fairness metric, which is written here, which is summation over the users log of the rate to each of the users. Now, these are the inside is the objective k, and they are combined as summation log of the rewards, and that is the nonlinear metric. The constraints are, of course, the resource at each time has to be given to only one of the users, so they are indicator variables summing to 1. So this problem is a assignment of users connected to the base station based on a fairness metric. And this is one of the example of multi-objective optimization, where you have multiple user rates as the different objectives. Any form of fair decision making will have nonlinear concave metrics, because fairness by definition needs to have a concave metric and not a linear metric of the long-term rewards to different users. So any form of fair decision making will have nonlinear concave metrics for long-term rewards, and we can have multiple examples of fairness. We could have proportional fairness, alpha fairness, Jane's index, maximum fairness, or any other measures we can come up with. The key is that if you have any form of fairness metrics, the overall reward will not be linear with time. Now, in the past, people doing decision making, especially in the reinforcement learning literature, assumed that the reward is linear in time. So let us see what are the challenges the nonlinearity brings into the decision making. So the first key result is that deterministic policies are no longer optimal. So in standard reinforcement learning or standard decision making, if you are in a particular system state, there is a unique action that is optimal. And that allows the use of dynamic programming, where we can basically prove that there would be a unique action that would give us the optimal results. And we can prove using the same Bellman equations or dynamic optimization optimality conditions, which reduces the optimal policies to be deterministic. Deterministic means in a given state, you have a single action that is optimal. Now, if you have a fairness joint function, let's consider the base station scheduling example. A single state of the system. So assume that all the users have the same channel, doesn't change with time. So everything is equivalent. So there is no state of the system. So there is no channel which changes with time. In this case, if you use a deterministic policy, the state does not change. The deterministic policy will give resources to one of the users because the state is the same. The deterministic action will choose one of the users. And if you choose one of the users and you optimize summation log rate, it becomes minus infinity because k-1 users are not getting any resources. So log of 0 is minus infinity. So deterministic policy does not work even if there is a single state in the system. So the optimal policy has to be randomized. Like for this fairness example, it has to give nearly equal resources to all of the users. So that can only be achieved by a randomized policy for a single state. So you can extend the framework to multiple states. And this is basically mesh plot showing that policy given state 1, policy given state 2, and the deterministic policies are on the extremes. And you notice that optimal policies come somewhere in the middle, which also say that optimal policy is not deterministic in general. And this can be seen because the optima does not lie on the vertices of the probability simplex. Okay. So in addition, we have the reason of why deterministic policies are not optimal intuitively. So again, for fairness function, we just saw in the previous slide that the optimal policy is not deterministic in general. And the key reason is that when you decide on resource allocation, it depends upon all the past allocations and not only on the current state. So even if you had a single state, it does not matter where you are. It matters who all got the resources in the previous time instances. And since the entire history matters, we cannot directly use a Markov policy, which is just based on the current state. Okay. So the approach to combine past, we can have a approach which combines the past states and actions that you have taken into the current state and make it a non-Markovian decision process. However, this non-Markovian decision process has exponentially large state space because you have to consider all the past states and actions, and you have to fix the time because the complexity is exponential in the time. And due to such a large state space, it cannot be optimally solved. There have been specific aggregation functions which can be based on functional knowledge. So for certain class of functions, you can come up with an aggregation function of taking the past states and actions into the current state. But the common thing is any form of such aggregation will still make the state space infinite. So the guarantees will not work even if that can be done. So to set up the problem more formally, let's say S is the state space, A is the action space. And the policy is for a given state and action, we have to define a probability of choosing an action A in state S. So as we discussed before, the optimal policy is probabilistic and no longer deterministic. And since we have the nonlinear joint function, the Bellman equations do no longer apply, which means dynamic programming and deterministic policies do not work. And this is essentially the reason that Q-learning gives us deterministic policies, and similarly DDPG, double deterministic policy gradient, also gives us deterministic policies. These fail on this problem because they rely implicitly on the Bellman equation to work. Okay, so let us see if we are using standard RL and implementing the system. What is one approach one can use? One approach one can think of is, let's consider at every time, I only consider rewards I have achieved or the overall utility I have achieved till that time as my objective. Okay, so at time D, this is my overall objective, where this is the average rate I have achieved till time D, aggregated over the user with the fairness metric. So I could have used this, but then there would be a summation over D outside because overall reward will be linear. Doing this type of system, we can have a Q-learning applicable. We could use the Q-learning DDPG or all those things. Even though this is still not a completely Markovian setup, reward is still not a function of current state and action because the reward depends upon all the past. So since the reward depends on the past, the regret or convergence guarantees still do not hold, but this is one way you can implement the system even though there are no guarantees for this to work. This is just a heuristic, and we note that it may not perform well. And we will show in our evaluations that this strategy is not good, but this is one thing that can be used in the system. Our proposed strategy will significantly outperform the strategy mentioned here. So this is kind of a baseline for us. To summarize the system again, so S is the state space, A is the action space. We are finding a policy which finds the probability of taking action A in state S, and the expected reward of the user K, or the objective K. So this is the reward the objective K gets till time tau. With 1 over tau, this is the average reward of objective K. Limit tau going to infinity is the infinite horizon average reward of objective K, and we do the expectation over the transitions. You have an initial state distribution based on rho 0. You have a policy and your state evolution. And the objective is to find the optimal policy which optimizes the function of the rewards of different objectives. Is the setup clear? Okay. So as we just mentioned, the overall objective is to find the optimal policy, which is maximizing the function of average rewards the different objectives get. The notion of regret is defined as the optimal. So this is optimal if we knew everything. If we knew all the transitions, we could compute all the expected values and everything. So optimal minus what we have achieved. So this is what I achieve in a finite time horizon T. These are the average rewards I get for the different objectives, and the overall function is what I achieve. So whatever is optimal minus whatever I achieve, the difference among them is called the regret till time T. And our objective here is to optimize the regret. So the key approach, we first consider a model-based approach. Model-based approach means that we estimate the model parameters and then assume that the parameters are known. Of course, we would be refining the parameters as the process keeps on evolving. So if I know the system transition probabilities, then the problem can be casted as a convex optimization problem. The way we do that is in terms of steady state distribution of state and action pair. So d pi is the stationary distribution. Based on the stationary distribution, the average reward of objective 1 is the reward you get in a particular state and action times the steady state distribution of being in the state and action summed over state and action. That is kind of the expected reward of objective 1. Similarly, you have expected reward of objective K. So we are maximizing function of overall rewards and optimizing the steady state distribution of state action pairs. The constraints are, since it is a steady state distribution, after one transition, the thing should be the same. So if you are finding the overall steady state distribution of state S prime, it should be with the one transition, it should be fine. So if you're transitioning from any S steady state distribution of S with evolution. And since these are distributions, the sums are 1 and these are non-negative. If notice that all the constraints are linear and the objective is convex optimization. So this is overall a convex optimization problem. The key challenge in doing this optimization problem is this transition probability. The transition probability is not known and it needs to be sampled. So there are two key challenges.
I had a doubt actually. Where is the dependence on time here, which you had?
Time dependence is not there in this optimization because we kind of the stationary distribution takes a long time horizon. Right.
Okay,
so when you have so you kind of assume that you are in a steady state in that sense. Does that answer the question?
Yeah. Okay.
Okay. So of course, the time dependence will come intuitively because this is assuming that we know the model. Now this P S prime given SA will need to be sampled. So you'll have an estimate of this. Now this estimate will be where you get the time dependence, because unless you know the estimate of this transition probability will get better and better with time. And this is what will change the procedure at every time. Because you will sample it, you will get a better estimate, you will run this optimization, and that gives you another data point based on which you will update this and keep on going. Okay. So as I just mentioned, so this is basically explaining with the time index because the policy has to keep on going at every time. But the key things are, in each time, we need to estimate the transition probability. And the estimation is based on posterior sampling with Dirichlet priors. So we are basically using Dirichlet approach for sampling. So this is a standard Bayesian sampling approach. And based on the estimation of the transition probability, you find the steady state distribution. And once you find the steady state distribution, then your policy is just a normalization form of the steady state distribution. Now, in each time, you basically come up with estimate of the probability and then solve the optimization, compute the policy, keep going back. The reason for using Dirichlet priors essentially is that even though we are saying that we solve the steady state distribution must exist. And in order for steady state distribution to exist, the Markov chain needs to be ergodic. Okay. And the Dirichlet priors, the way they work is they initialize everything to 1. So you'll see the initializations with 1, and that's why you have max 1s everywhere. So what it kind of does is it does not initialize the visitations as 0, but initializes the visitations as 1. And since you initialize everything by 1, and when you normalize, additions of 1 in the numerator and denominator will not make any probability 0. So you'll have any policy, based on any policy, the Markov chain will be ergodic. So the steady state distributions will exist, which is a key to show that, the results, because if the steady state distribution does not exist, then the feasibility of the convex optimization does not happen. Okay. So to summarize, we estimate the transition probabilities using posterior sampling with Dirichlet priors. At every time you estimate the transition based on the samples till that point. This guarantees existence of steady state distribution. You basically have to come up with when do you stop. So there are stop in the sense you will have time and then epochs within the stopping conditions. So we basically use an epoch condition, which is standard doubling, because you don't know the time. So you keep the standard doubling trick on the time, and you can get the regret for any time algorithm as decreasing as 1 over square root t. So L here is the Lipschitz parameter for the concave function. D is the diameter of the MDP, A is the number of actions, K is the number of objectives, S is the number of states, and T is the time. So the key thing here is the approach mentioned here gives the overall regret as 1 over square root t. You achieve a sublinear regret for any time t. So to summarize the results so far, we gave a model-based approach for multi-agent reinforcement learning with the joint reward function. This is the first result on regret bounds for infinite horizon setups with or long-term time setups, long time horizon setups with joint objectives. And the formulation for general functional form is new with multiple objectives. The issue that this approach faces is common with every model-based approach in the literature, is that you have a tabular structural form, which is why you were able to do the optimization. So the optimization goes over optimizing d pi SA for all SA. So you have number of variables as S times A. And if the number of states or number of actions go large, the problem is complex and which makes it non-scalable. Any questions so far? Okay. If not, then we have already discussed the model-based approach, and we mentioned the issue that model-based approaches, even though have good convergence and regret guarantees, they're not really scalable. In order to deal with such challenges, we usually propose model-free approaches, which parameterize the policy functions, and we can get scalability using the parameterization functions as neural networks or something of that nature. So we'll now study the model-free approaches for solving such problems. So for a model-free approach, we again use the same formulation. J's are the rewards. We parameterize the policy as pi of theta. So theta are the parameters. Think of theta as the weights of neural networks, and the policy parameterized by the weights of neural network. And we are optimizing the weights that optimizes the function of average rewards of different objectives. So the model-free approach solves the problem. So you have this optimization problem with respect to the weights of the neural network or parameters of any policy function. And we aim to solve this problem by applying policy gradient. If we are doing the policy gradient, the key thing is we need to find the gradient or an estimate of that, because the dynamics are stochastic. So we have the gradient of function. So as you notice, we have objective as the function. So the gradient will be the gradient of the function. We could apply the chain rule with respect to J's, because the function is a function of the average rewards, and the average rewards are for each user. So we apply the chain rule, del F by del J times del of J. The second part is the standard part, which is there in every RL type algorithms, but the first part of derivative with J is the new part. And of course, summation over K, because you have multiple objectives. So even if you ignore summation over K for now, for single objective, this is still new. So we could use policy gradient theorem to get an estimator of J. And if we do that, the estimator actually turns out to be something like this. The challenge here is that first, the expression for the gradient of the function has a term which is del F by del J. This is also not known. we need to estimate this parameter because we need to estimate at the particular theta. So this estimator is not available because of the non-linearity of the function. And the second challenge is you have infinite summations and they cannot be calculated. You need to truncate them. So if there were no function, then this was 1 because del j by del j would be 1. Because if function is trivial, then f of x equal to x. So f of j will be j. So this will become del j by del j, which is 1, which is there in standard policy gradient. So you don't have these terms. So truncation is still used even in standard policy gradient, but this function complicates the problem. To solve the first challenge, what we do is we come up with an asymptotically unbiased estimator for del f by del j. And in order to do that, we have to independently sample this. And the reason to independently sample is that we don't want any correlations between this estimator and the overall estimator of the problem. For the second challenge, we use the standard techniques of truncation based on episodes. And doing that, we can come up with estimators for the overall value function where we take the estimator of j's here. So using these estimators, the key thing is that the estimator is no longer unbiased. It is asymptotically unbiased, but there will be a bias for this estimator. And the bias essentially comes from the nonlinearity. And that actually creates the key challenge in the proofs to efficiently handle the bias terms. And the other thing that complicates the proof is we had to have a double loop because we need an estimator within an estimator. So which is why there are two terms of N1 and N2. N1 is the estimator for the outside loop, N2 is the number of samples you have to collect for the outside, N2 is the number of things for the inside. So you have a kind of double loop type estimator here. So the key result that we can get is that the approach that we mentioned gives us optimal algorithm if you sample a certain number of trajectories. So overall, it says that if you sample 1/epsilon4 trajectories, you get the optimal result within a bias term. So this bias term essentially is how good your policy function is. How dense is it? So you have to approximate the general policy with the functional class. How good could that approximation be? If we use Gaussian process or Gaussian function or a softmax parameterization, we can prove that epsilon bias is exactly 0. So you don't have anything extra. And if you have a linear MDP structure, you again do not have any epsilon bias. Epsilon bias will be 0. So any of the good cases, we don't have epsilon bias. So you get the optimal within 1/epsilon4 trajectories or epsilon optimal within 1/epsilon4 trajectories. If you're using an incomplete parameterization, then the gap may be positive. But of course, as we know, neural networks are dense enough. So denser and denser neural networks you choose, epsilon bias will keep on becoming lower and lower. So the first term is the term which can only be controlled by functional parameterization, and second term can be controlled by sampling more and more trajectories. So to summarize the results, we have parameterized policy based results with policy gradient. The key thing that we did was proposing a asymptotically unbiased estimator and then using that with the formulation to prove the results. The results are applicable to both tabular setting as well as continuous state space. So the approach is scalable because it can work for general state space sizes. So we for now proposed both the Q-learning based algorithms as well as the policy gradient based algorithms. We can actually also come up with actor-critic based algorithms. The key thing in actor-critic is we have to compute a bias with which we can reduce the variance of the policy gradients. So we come up with bias calculations, which are all function dependent. For details, we can see the paper, but I would be skipping these things. But the key idea is the approach can actually be extended to actor-critic algorithms where bias could be subtracted. Okay. So any questions still for model-free algorithms? Okay. If not, we'll go to the next part of the, yes.
Participants are requested to unmute yourself and ask questions, if any.
Okay. So in the next part of the talk, we will go over to constraints. So far, what we did was we balanced multiple objectives using a concave utility function. Now we basically say there are rewards and there are also constraints. This could happen in multi-objective or standard RL setting. So we actually consider a general multi-objective setting with multi-objective constraints. But to keep the exposition simple, we consider a linear one in this slide. But as you will notice, everything can be generalized to multi-objectives. There is no limitation of that. So in terms of constraints, you have the same way as we had the distribution function of state and action. The constraint you get in a particular state and action, average is less than C. Again, if you have to make it a functional form, you can have a GI of the multiple objectives the same way. All right. So based on this type of setup, you can again have the optimization problems the same way. So this is the maximizing of the objective, which you could also add the function if you have different objectives. It will be convex, and you will again need to have convex constraints if you do the function. And the rest three constraints are straightforward, which are existence of steady state distributions. Now, as you can see, based on the simplicity of the optimization equations written here, that the entire posterior sampling based approach that we gave before for the model based can be extended to this setup. So we can handle general constraints and we can get similar regret guarantees. So the key challenge that constraint gives is you can define the achievable reward for the objectives the same way, achievable rewards for the constraints. The reward regret is defined exactly the same way as before. However, constraint regret is defined differently. And the reason is for rewards, you cannot not satisfy the optimal. So you have to be, you are doing better by achieving better rewards. But in constraints, if you're satisfying the constraints, we don't care how well you are satisfying the constraints. We only care whether you are not satisfying the constraint. So we need a positive sign, which is a max of x comma 0, to say that we only care about the constraint violation and not whether you are satisfying the constraint very well at certain times. So the key intuition is there could be a policy that satisfies the constraints in even times and does not satisfy the constraints in odd times. And the positive and negative terms could balance each other. And we don't want that. We do want that you being dissatisfying the constraint to be taking a priority. So which is essentially why you have the plus sign here. Okay. So again, we use the similar framework. So the regret could be bounded, but constraint violation get a bit tricky, but we were able to show again that the constraint violation also goes as 1 over square root t. So you can get the same bounds for objectives and constraints here. So now we go over to the evaluations. So the first setup we consider, sorry, there is a chat message. Okay, sorry, not for me. So there are k queues. We have arrival rate at different queues. At qk, arrival rate is lambda k. And all the queues are served by a single server. So this is like the base station scheduling. You have multiple queues coming into a single server, and the question is which queue user to be serving next. So think of this as a processor scheduling. You have multiple cores. You have computation jobs coming from multiple cores, and then you are deciding which core should you process next. And this can be used in processor scheduling, traffic management. In traffic management, you have, let us say, a four-way stop sign or four-way light, and you are deciding which side user to let go next. You have queues building up on the different lanes. So this is a standard abstraction of these type of problems. And then the reward of a queue is 0 if the queue is not selected, and the reward of the queue is 1 if the queue is selected. And overall, we want to be fair to the different queues or lanes in the traffic management setup. So the overall reward metric is similar as before in our running example. So to see the results, let's start from below. So the bottom two are the standard policy gradient and queue learning algorithms. The standard one where reward till time t is taken as the objective at time t. And the blue one is the standard actor critic. And at the top are our proposed algorithms for actor critic and policy gradient. There is not much difference between actor critic and policy gradient here, but the key thing is that the proposed algorithms far outperform the classical algorithms. Okay, so the baseline actor critic policy gradient assume the reward till time t as the reward at time t, and the DDQN based approach assume deterministic policies, and that's why they are not working well. That's why DDQN is really at the bottom. Okay, followed by the actor critic policy gradient standard, and then our algorithms. Next, we take example of network traffic engineering. So you have a network in which you are deciding the routing, and you are getting multiple demands with source and destination and amount of traffic, and you have to basically determine which route does this demand take. So for example, if you have source here and destination here for the demand, you could take a route like this or like this. You have certain capacities of the link and certain demand profile based on which you are deciding where to send it. So the problem is to compute forwarding paths with multiple demands. We consider each demand as an objective. The state is based on what we are taking the decision, which we take as vector of load ratios on the link, how much each link is loaded at that time. And the action is forwarding path for each request. Reward is 1 if the traffic demand is satisfied on the path, otherwise you are not routing it well. And in order to consider the evaluations, we consider a abelian topology, which is one of the standard topologies for Google infrastructure. And it has 11 nodes, 28 links. To consider an example, we take uniform bandwidths between 40 and 60. For traffic, we consider 6 random source destination pairs, and the traffic is also taken as random, uniform. So in this result, we compare the proposed approach with the baselines, and DDQN is the lowest. So this is a log fairness metric. So take these numbers in exponential. You'll kind of see the differences much more than you can see on the logarithmic scale here. Then this is the standard policy gradient. And the proposed policy gradient is significantly above the standard policy gradient. And this is the standard actor critic and the proposed actor critic formulation. So what we see is that the proposed algorithms outperform the baseline. The proposed actor critic is significantly outperforming the standard actor critic. The proposed policy gradient is outperforming the standard policy gradient. And other thing you note is that the proposed algorithm go to convergence much faster. So they learn the procedure very quickly compared to others, which take time to learn to even go to some reasonable outputs. And as again, the deterministic approach does not work. So that's why it is not even comparable to the other approaches. To conclude the talk, we provided a new formulation for nonlinear optimization of joint reward functions using reinforcement learning. We converted the approaches for non-Markovian problem into Markov-based algorithms. We gave new model-based and model-free algorithms, provided the guarantees of both of them, showed that they achieve state-of-art results. In the future, we need to care about if we are talking about these networking scenarios with multiple agents rather than multiple objectives. Distributed implementations are needed, and we need to extend things to more general applications because the framework is very general for any forms of objectives. In terms of other ongoing works in the group, we are working on improving the convergence rate for the policy gradient setup. So currently we have 1/epsilon4. We are working on improved variance estimators to see if they can be used for this setup. Recently, there has been work in convex optimization where we can achieve zero constraint violations. Zero means order 1. And we can have the same objective regret. However, using that on top of our setup is a bit challenging, and we are working towards that. And the key future work that we haven't started yet is to make the algorithms distributed. What we believe is especially the model-based approach is an optimization problem, so we could use those techniques to make distributed. However, the learning of the state evolutions will also need to be thought of, whether they are joint states, how to learn those things. So those are some of the key challenges left for the future. So thanks everyone. These are some of the works based on which this talk was based. Any questions would be greatly appreciated.
Thanks, Vaneet. Rajesh here. I have a question.
Sure.
So in the policy where you had constraints being violated, but the violations were less than or equal to, you had an appropriate constraint, appropriate upper bound that was growing with time. So the question is, in those situations, did you know when a particular action was taken that the constraint was violated? Or is it something that you get to know after the fact?
It's something you get to know after you take the action. So the constraint violation function is assumed to be known, but of course, after you take the action.
That what is assumed to be known is once you take the action,
you know the violation
constraint was violated. Or
you get the amount of violation.
Or get the amount of violation. So if it is a scalar constraint, for example, then you straight away know what the constraint is. So from the next time
yes,
on,
you can put it for known constraint, but we generally assume that the functions are unknown. So we did not assume that the function is known a priori. So you can query it, but you don't know it. But yes, if you know it, the same approach will still work.
But when, in the scalar case, when you actually give the information by that says you're violated by this much, you're pretty much giving the constraint also. So
yes,
it's as good as
so you
one
can learn
sample.
it.
Yeah, you can learn it, and exactly, yeah, because
yes,
when
and
you
that does not
violate,
change anything. Yes, if you learn the functions, the definitions still work. So even if it is known or unknown, that does not matter for the reward functions and the constraint functions.
And this is because you're only looking at these upper bounds.
Yes, and the main thing here is basically the transition probabilities which are unknown. Right, so the transitions will still be unknown, and so you will still not be Means that is where the key analysis lies, is sampling the process of the MDP. But yes, if the rewards or constraint functions are known, that does not change the results.
I'll wait for others to ask a question before coming back.
So thanks, Vaneet. I have some very simple question actually for you. So when you say policy gradient, so policy typically means that for every state you have an action in mind, right? And so in this setup, when you say policy gradient and you only take say one action, right? And then you're going to change your policy, but because you observe only, the result of one action, you're probably going to change only in one dimension, right? With which state which you observed, and you're only going to change policy for that state, right? Is that correct? Or what do you mean by policy gradient here?
So let's go back. So what we are doing in policy gradient is you are computing the gradient of the function. So yes, so once you, so it's basically also the function you are optimizing, change at one changes. So think of a continuous space, right? So you are changing thetas. Thetas does not change for a single state and action. The weight changes everything, changes the policy for everything.
I see. Okay. Understood.
Right. So if the neural network architecture changes, then it does not change locally.
Right. Okay. Thanks, Vaneet.
Vaneet, one more question.
Sure.
Rahul Singh, who is our faculty member, he has been looking at this reward biased approach, where he's actually introducing a bias and something along the lines of the you're optimistic under uncertainty. And so those which have higher reward, you bias them upward.
Yes.
So he's been looking at some such policies. It might be good to compare your strategy, which I think it began with DDQM.
Yeah, so actually those are what we are also thinking towards. So if you notice in our model-based algorithm, we assume Dirichlet priors.
Yes.
And the Dirichlet priors were kind of used to get away for the problem to get the stationarity. And actually those optimistic samplings and those bias things can help us reduce those assumptions. And we can get things, of course, the complexity increases because you have to search over an optimistic policy space, which is larger. But yes, that gets rid of the assumption of the Dirichlet priors. So we are actually thinking towards that to see whether we can get the satisfaction and other things working with removing the prior assumption.
So the Dirichlet prior, I thought it was the conjugate prior for your Bernoulli.
Yes, but the priors could be relaxed. So you don't need basically, so it becomes a constrained form of regret definition with the certain priors. So we could make it more general.
And your choice of the parameters, I felt, was geared more towards ensuring that your system is ergodic.
Yes, and optimistic can give us ergodic for free.
Optimistic can give us ergodic for free. Okay.
So using optimistic approaches, we could again get ergodic structures. So that is what we are looking towards. We haven't still finalized the details, but we are still working towards the proofs of them. But at least that is one way we can use it easily in terms of basically relaxing the assumptions in the model-based approach.
Okay, so if you haven't used a certain action at all, then you don't know anything about that action. So your optimism will essentially explore that option. And that naturally
and that is why you would basically still not get stuck. And that's why the policies will still be among the, that's why ergodicity might still hold.
Okay, yeah, thank you.
Thank you, Dr. Vaneet Aggarwal, for a wonderful talk. If there are any more questions, we can still take 1 or 2 questions. We can still take. Or you can put it in the chat box if you have any questions.
Yeah, you can feel free to send me an email anytime.
Yeah.
Thanks a lot, Vaneet. I think.
Thanks everyone for attending. And great
So, yes. Yeah. So we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the webpage. Thank you, everyone. You all have a great evening ahead.
Thank you.
I think they have to. Pritam, are you there? Can